Okay, good morning. No test today. Um, we'll start there. So hopefully everyone got my announcement. If not, well, I didn't hear back from anyone who was super upset about moving the tests. So and like I said in the announcement, usually I'm not too keen on moving test dates. It just feels weird. But in this case, it sounded like everyone was kind of on board. So test 2 has been moved. Oops. To the weekend. I know that's weird. It'll be available Friday after class until Monday at midnight. So if you have busy weekends or whatever, then hopefully you'll be able to find some time on either the Monday or on the Friday. I guess those are reversed. And so it'll just be an open quiz. Yeah, more time to study, more time to worry about it. But it's good. So what's nice is, yeah, you can practice a little bit more. You can work on those assignments a little bit more. And yeah, so hopefully everyone's okay with that. So it's moved to the weekend. It will be opening after class on Friday and closing Monday at 11:59. Okay, it's going to be a time test, so you still just have the hour and 20 minutes. It's just that you, oh, you're welcome. It's just that you have to pick a time where you can sit down and you've carved out an hour and a half at least, because an hour and 20 minutes for the quiz, and then exactly, yeah. So from Friday to Monday, and let's see here. Yeah, so it's a timed quiz. You are submitting your work. And so I couldn't figure out a way to have it done automatically in Moodle. That's okay. What I'll do is you'll have 10 minutes after you submit your quiz. So I can see the time that you submitted your quiz, and then I can see how long after you submitted your work. You'll have 10 minutes, okay? Because that's what we were going to do in class, and so that's what you're going to have. So it is going to require a little bit of legwork from my side. That's fine. I'm okay with that. So it's 1 hour and 20 minute time test. Okay, completely open book, just like class. How many questions? So I haven't done the run through for the timing. Right now it's at 20 questions, and there is a long answer question in there. I'm not ready to commit because I do have to do the timing, but as soon as I sent out that announcement and I didn't hear anything, then I moved on to other things. So I'm like, oh, well, now that I don't have to do that until Friday. No, probably Thursday, but so I'll try to do it as soon as I can, maybe before class on Thursday. But so I've got it at 20. I'm feeling good about that length, but I have to run through it, and then I take my time and I multiply it by 3 for you guys. And usually that's a good amount of time. You still have to keep your pace up, right? We can't be, I can't give, super short tests. I'd rather have lots of questions and then cut it down after the fact than for you guys to just have, all this free time to, research too much. You're supposed to know the answers, right? And know how to solve them. So there's a fine balance there. Okay, so it's going to be a time test. and 10 minutes to upload your work. Okay, so you'll have to scan and upload. I'll say that. To scan and upload your work. Okay, so definitely practice, you know, your scanner app or whatever, so that you're quick at scanning. Honestly, to scan the work that you're doing, it should take about, you know, a minute. Okay, so if you're spending more than that, then you need to practice scanning, and you need to practice, you know, importing your file and being able to upload it to Moodle. Okay, so make sure that you're prepared for that. Okay, and oh yeah, so your work, just there's one long answer question. Oops. Where you have to show all the steps, all your work. Of course, it's going to be a hypothesis testing confidence interval question. Okay, so you have to show all your work and show me that you know to follow the steps. Okay, so there's one long answer question for marks. For marks, but also include, maybe I shouldn't say submit, also include the short answer questions. Okay, so there weren't no chi-squared long answer question. No, it'll be on, yeah, no. There will be chi-squared questions, but no long answer chi-squared questions. Just multiple choice and you know, fill in the blank situations. Okay. So also use your work, right? So also submit the questions that you've submitted on Moodle, right? So in the Moodle quiz, as a record of what you submitted. Okay, because last time there were a couple of people who you know, the answers didn't submit properly for whatever reason, right? And so just to have a record of the answers that you submitted. Also use your work, or also write the short answer I guess options picked / submitted as a record, right? And I talked more about it in the announcement, right? But just make sure that if there's any problems, then, and I see that there's an empty answer, then I'll go back and I'll check your submitted, your written work, right? And then I can give you those marks if it's correct. If not, I'll mark it wrong, right? But then I can at least, you know, go back and double check, okay, if there was something that wasn't submitted. Okay. So kind of weird. I've never done a test like this. I usually just like to use class time. But on the plus side, and probably the selfish reason that I was okay with moving it to the weekend instead, is because it gives us more class time to cover class material. I was going back and forth about, okay, fine, we'll move it to the weekend, but then it's going to cover this week's material. And I decided, no, we'll keep the same material, okay, as the cutoff from last day. So test number 2 will still only cover, I'll put only in quotes. Yeah, I'm gonna love what you guys put out there, I'm sure. We'll still only cover the material up to the end of last day. The material up until the end of last day. Okay. Yeah, so you do need to move quickly through these questions. Okay, so right, keep an eye on the time. And so I am designing the test that you do have to know the answers. So you can't rely on having to look every little thing up. Unless you're confirming something, then that's good, and that usually it doesn't take as long, right? So now is not the time to be learning concepts. You should just be able to read the questions and be able to answer them without open book, right? But it is open book, so you can go through and you can check your work and you can check your logic, but the idea is you should know these questions and just run through them. Okay, so definitely keep your pace up, right? That's important. Okay, good. Any questions about the test? I know things got weird, and if you didn't see my announcement and you're really upset about it, then please send me an email and we will figure something out. Okay. So, okay, we talked about, where's the end of this page here? Huh. Oh, I didn't write very much, did I? All right. So we started talking about one sample means questions. And so we started talking about numerical data. So in terms of review, right, we started talking, analyzing numerical data. Because we've been focused on categorical data so far, right? And for categorical data, we talk about proportions, and we looked at, okay, if I have one sample proportion and or just two categories, then I can use a Z test, right? I can calculate a Z. If I have more than two categories, or if I have more than two categorical variables or some mashup of that, then we use a chi-squared test, right? So we saw a Z test, we saw a chi-squared test, and it depends on the type of question that we have, right? So now we're moving to numerical data. We're going to do the same thing. We talk about the different types of questions. Okay, so we're going to finish talking about one sample mean questions today, right? And then we're going to move into two samples. Okay, so what if I have two samples? Ironically, there are two ways to have two samples, so we need to introduce those two question types. Okay, and then what if we have more than two means that we want to compare? Then we move on to an ANOVA. But for the first few, we use what's called a t-test, which means that we're using the t-distribution. So analyzing numerical data means that we are analyzing the mean, or means if we have multiple samples. Okay. And so we will see, maybe as a nice overview, let's just list the question types and then we can work through them. Okay, so we will see 4 question types. For numerical data. Wow, this is so annoying. I've got an Apple Pencil and it's acting like it's running out. How weird is that? I think maybe my little tip is gone, or I don't know. They like to make it feel like a real pencil, I guess. So we'll see 4 question types for numerical data. Okay, so the first one is one sample mean. Okay, and that's where we're starting, and that's what we started last day. We started talking about the t-distribution. And maybe I'll do this. Oh, I don't know why I erased that. I wanted to scoot it over. Wait. There. So we'll start with one sample mean and we compare it to some hypothesized value, just like we did with proportions. Okay, for two sample means, they can be paired. Okay, which means that what we'll see is that we have two observations or two records for each row, right? Or two observations on each subject, which behaves slightly differently than two sample means that are independent. Two sample means that are independent. Then these two samples, right, are coming from two independent groups and there's no way to naturally link observations, then we can treat them as two independent samples. Okay, and then the fourth one is more than two means. Okay. Now, for the first three here, we use a t-distribution or a t-test. Okay. For the last one, we use what's called an ANOVA, or it uses an f-test, but usually when we refer to it, we talk about an ANOVA, an analysis of variance, which is weird because we're actually analyzing more than two means in this case. But we'll get there. Okay, so those are the different types that we're going to introduce. And so last day we started talking about, okay, the t-distribution, what's special about the t-distribution? And what we landed on was that, okay, we know, or we're given the sampling distribution of X bar. The sampling distribution of X bar is that X bar follows a normal distribution with a mean mu and a standard error of sigma over root n. Okay, but we don't know the mean. Okay, and just like before, when we had the sampling distribution of a proportion, then we said, okay, well, we don't know the population proportion, but I do know the sample proportion, so I'm going to use that instead to estimate it. And then I can find everything that I need just using the sample proportion. Now we're going to estimate this with estimate mu with X bar. And we estimate sigma over root n with S over root n. So notice how we're using two pieces of sample information. Okay, so the problem becomes, okay, well, if I collect a new random sample, then my new random sample of size n is going to have a different mean and a slightly different standard deviation than my previous sample, right? And so now I've got two things that are changing with every sample, with every new sample that I could potentially collect. We only collect one sample, but we need some way to account for, okay, just because we found this sample mean and this sample standard deviation, well, that doesn't mean that that can't change with a different random sample, right? And so we need this distribution, and that's what makes the t-distribution a little bit different, okay? And we understand that if I change the sample size, then of course my estimates are going to change, right? And if I change the sample size, so more specifically, if I change the sample size towards the population size, right? So if I increase my sample size, then my estimates get closer to the population mean and standard deviation, right? And so the t-distribution takes the fact that we're estimating two things into account. the t-distribution takes the fact that we are estimating both mu and sigma into account. Okay. And because our estimates x bar and s depend on the sample size, that is the one parameter of the t-distribution. Since x bar and s depend on the sample size, or maybe the estimates, no, let's just say here, I'll just say in brackets, the estimates or the reliability of the estimates depend on, and the sample size depend on the sample size n, the t-distribution has one parameter, and that is the degrees of freedom. The t-distribution has one parameter, which is the degrees of freedom, which we call df. Now, for one sample mean, the degrees of freedom is n-1. Okay, so as we introduce these question types, I'm going to need to tell you, right, if we're using a t-test, I'm going to need to tell you how you find your degrees of freedom. In fact, if you look at that formula sheet that I posted, it's kind of, it's for stat 121, 124. And so it's missing a couple of things. You might have noticed it doesn't have the chi-squared test, but it does have most of the key tests that we're doing, especially for these t-tests, okay? So it has the degrees of freedom on there. Okay. So the degrees of freedom is n-1. Now the degrees of freedom dictates the shape of the t-distribution, okay? For small sample sizes, it leaves a lot more room in the tails, and room in the tails means that there's a higher probability, or we're allowing for a higher probability of those things happening, because our sample size is so small that we don't have that reliability in the estimates. So we make room in the tails saying, okay, well, I can't rely on my estimates. And so these might be way off, and this observation might not be as extreme as it seems, okay? So the degrees of freedom determine the shape of the t-distribution. Okay. And so for smaller n, so for smaller degrees of freedom, the area in the tails is thicker, right? And so we call those fat tail distributions. But what happens is it closes in on the axes relatively quickly, okay? And so we don't actually need huge sample sizes for it to look approximately like a Z distribution, okay? But we still have to use the degrees of freedom if we're using a t-distribution, okay? And so for small degrees of freedom, the area in the tails is large to show that those extreme values, they have a higher probability of happening, to show that extreme values have a higher probability of happening since our estimates are not as reliable for small sample sizes. So since our estimates are not as reliable for small sample sizes. The conditions for a t-test are very simple in comparison to a z-test for proportions, right? That's when we had to check, okay, do I have a random sample? Is my sample size less than 10% of the population? Are my observations independent, right? And then do I have at least 10 successes and at least 10 failures, or expected successes, expected failures, and so on and so forth. There were a lot of hoops we had to go through, right? I guess this is kind of, the review ended, let's say the review ended somewhere around here. I forgot. It all rolls into one, I guess. So, what was I saying? I'm drawing a complete blank. I wish I could do an instant playback on what I was saying. I felt really passionate about it, and now I can't remember for the life of me what I was talking about. Anyways, oh, the conditions. I don't feel passionately about the conditions. Maybe I do. You know, when there's a feeling like, oh no, I was really into what I was saying. Can't remember. So there are only two conditions. Two conditions we need to check in order to conduct a t-test. So notice that, okay, so for all these first three question types, one sample mean or two sample means, regardless of if they're paired or independent, we're going to do a t-test, right? And so the conditions that we check for all of these are going to be the same. Now, if we have two samples, then we need to check it for both samples, but that's okay. So the first one is independence. Independence. Okay. How do we check independence? Well, was the sample randomly selected, right? If the sample was randomly selected, we can assume the observations are independent. The observations are independent. If not stated, we must assume. That is what, you know, the conditions, sometimes we call them conditions and sometimes we call them assumptions. So what gets confusing for a lot of people is, okay, well, it doesn't say that it was randomly selected, so I can't assume independence. That's not what we're doing here. We're saying either it says, and then we feel fine assuming independence because it says that we collected a random sample, great. If it doesn't say that they collected a random sample, then you have to argue that, okay, well, it's reasonable to think that these observations are independent of each other, right? So if not stated, we must argue that we can assume the observations are independent. So in terms of the conditions, they actually stay the same, right? For the proportions and for the means questions, it's just how we check them is a little bit different. So the independence, all we're really checking is, was this sample randomly selected? Okay. For the second condition, it is a normality condition. Okay. But before, for proportions, we had to make sure, okay, do I have at least 10 successes, at least 10 failures, right? And then depending on if I'm doing a hypothesis test or confidence interval, I check different things, right? And so that gets messy, and it's just hoops we have to jump through. Okay. For normality, for means questions, we're only going to check if the sample size is larger than 30. Okay, there's a little bit more than that, but for sample sizes larger than 30, we can assume independence. We can assume normality and potentially independence, but I meant to say normality. Okay, so by the central limit theorem, if n is greater than or equal to 30, so a large enough sample size, we can assume that the normal distribution applies, right? So we can assume normality. There are some caveats there. Okay, so we have to be pulling from a relatively non-skewed distribution, okay, for sample sizes close to 30. But even for really, really skewed distributions, if I have a sample size of 200, usually, you know, I'm safe. So you'd have to collect a larger sample. But for us, I'm happy with you checking, okay, is the sample size larger than 30? Right? Typically, we go vague and we say the sample size is large enough, right? But it's nice to have some kind of hard line, okay? If the sample size is larger than 30, then we can assume normality. So then what you would say is, because my sample size is larger than 30, I can go ahead and assume normality, right? So here, if n is less than 30, we have to check to make sure that the distribution is approximately normal, right? We should check to see that the distribution of our data is approximately normal. Now, we're pretty flexible with this normality condition, right? And so if n is less than 30, we must either assume the data is approximately normal, right? Is approximately normal, unless we can check the histogram and or numerical summaries. To ensure we have a normal distribution. We have, an approximately normal distribution. Okay. But in the end, there are only two conditions, right? And it can be as easy as the sample was randomly selected, so I can assume independence, and my sample size is more than 30, so by the central limit theorem, I can assume normality, and then you move on, right? And so it can be that simple, or you might have to argue your way to it, but these are the conditions that we need satisfied. Okay, so what we said was, if we're testing the mean, then we are hypothesizing about the population mean, right? And so let's see here. To test hypotheses, and you know what, maybe what I'll do is I'll just bring in I'll bring in the formula sheet tidbits. It used to be chapter 5, now it's not. Now it's chapter 7. The content didn't change, it's just the order. Okay. So here, usually we talk about sigma being unknown because kind of the old school way of introducing these ideas was, okay, well, let's pretend that we know sigma. That's never going to happen in real life. So I haven't introduced that idea because it's never applied. You should never use it. So I don't want to kind of encourage bad habits. So we started with the proportions instead, which uses a distribution. Okay, and so sigma unknown really just means that we use S instead of sigma, right? So this is the only type of question that we have introduced, but one sample mean sigma unknown is usually how we refer to these question types, but we've only talked about this one sample mean situation, so this part is just extra, okay? Here, we're hypothesizing about the mean, the population mean mu, right? So our null hypothesis is that mu equals some null value, right? Some hypothesized value. So this mu naught is our null value. Again, we can set up our alternative hypothesis, and the only thing that's changed is that there's a not equal to sign here. That's for a two-sided test, right? Not equal to. And we can change that to less than or greater than, but as a default, we use not equal to, right? So here, default is a two-sided test. Could also be less than or greater than for a one-sided test, because then you only care about one extreme, right? If it's significantly less than or significantly greater than. I'm moving to the wrong sides, but that's okay. Okay, so our T, the T distribution, right, means we have to calculate a T. So here we have our point estimate. Right, so if we kind of zoom in on T is the point estimate minus the null value divided by the standard error of the point estimate. We said that, okay, well, X bar is the point estimate for the mean. The null value is mean mu naught, right? So how far is that sample mean from the hypothesized mean once I take into the spread? And because I don't know sigma, I have to use S over root n, okay? It's also got the degrees of freedom down here, right, as a little reminder. Okay. And we can build a confidence interval for the mean, right? So now we're trying to capture the population mean. So we build it around our point estimate plus minus some critical value T star times the standard error of the estimate. So for hypothesis testing, we calculate a T for a confidence interval. We have the point estimate plus minus some critical value times the standard error of the point estimate. Okay. Same layout as before. Okay, just different point estimates because now we're talking about something else, right? Not talking about the population proportion anymore, talking about the population mean. Okay, so we need to get used to the t-table. We've already seen it, right? And so now, because we used it to find the critical values for Z star, right? If we had to find a confidence interval for a proportion, then we needed a critical value of Z star, right? And so let's start there. If we have to find a T star, okay, we have already used the t-table as a shortcut for finding Z star. Okay. We find T star in a similar way. Okay. Where are those tables? Chi-squared table. No, this one. Okay. Let's see if I can grab this one. There are lots of different versions of this table. This one is a little bit more detailed than the one at the end of the textbook. Okay. But they all work the same way. Maybe I'll do this because I'm dealing with a page break here. Crop. There. Okay, so I'm kind of chopping it up here. Okay. And maybe what I'll do here is I'll copy this as one thing. Okay. So all these keep going, whatever. I just wanted to have it kind of readable on one page. So remember, for one sample mean, then the degrees of freedom, and I should have gone all the way, is n minus 1. Okay. One thing to note is we already saw it in the chi-squared. The chi-squared also has degrees of freedom. They were slightly different, right? It depended on how many categories I have, right? But the degrees of freedom are this kind of all-encompassing idea, okay, of how many things you're estimating. It doesn't matter, but we'll just flat out use the degrees of freedom. Now, if you find yourself having to decide on some degrees of freedom. So let's say, for example, you have 58 degrees of freedom. That means you have a sample size of 59, right? So given the choice between 50 and 60 here, right, you can see that the values that you're going between, the difference here is minimal, right? So what we do is you have to always round down to your degrees of freedom. So even if you have 900 degrees of freedom, you would still have to round down to 1,000 because you can't assume that you have a larger sample size than you actually do. Okay. So here, we must always round down if the exact degrees of freedom is not found or is not in the table. I'm trying to keep it on this one page there. Okay, so no matter how close you are, you always have to bump it down, and that's fine. You know, you can compare these values and you can see that there's really not that much change. Okay, what's going on here? The degrees of freedom are increasing until suddenly you're at Z. What's the idea here? What's the big idea here? Well, if I increase my sample size, at some point, I will reach the population size, and that's where Z is. Okay, so Z star is a T distribution with the population size -1 degrees of freedom, right? So the T distribution slowly approaches the Z distribution, right, which is stable. The T distribution kind of, it forces the tails down as you increase your sample size, and eventually you're fixed at the population size, and then you're at a Z, okay? So for example, if we have, let's say we have, so for example, if N is 59, then the degrees of freedom is 59 minus 1, which is 58, but use degrees of freedom equal to 50, right? Because when I went to the table here, I'm choosing between 50 and then it jumps to 60. There is no line for 58, so I have to use 50. Now, what that means is once I've decided my degrees of freedom, or once I've found my degrees of freedom, I can ignore the rest of the table basically, right? I'm going to keep these p-values, of course. So these are p-values, that's nice. And then I'm going to keep these confidence levels. Everything else you can ignore. Okay. Once you have found your degrees of freedom, you can't stray from this line. You can't stray from this line. Okay. So what happens? We notice that all these T's, so these are T-scores, okay, at 50 degrees of freedom. So all these T's are positive, but because T is symmetric about the mean of 0, then if we get a negative T, we can take the absolute value and we can only look, or we can look at the positive version of it. Okay. So if I have 50 degrees of freedom and I want to build a 95% confidence interval, then my T star would be 2.009. Okay. So for example, at degrees of freedom equal to 50, we find T star equals 2.009 at a 95% confidence level. For example, right? So that's how we're going to find critical values. Whereas before, right, comparing that to what we did before, if I want a 95% confidence level and I have a Z star that I'm looking for, then you just zip to the bottom, but now we stop at our degrees of freedom line. Okay, so what happens with these T's, because these are going to behave, or this table looks a little bit different. We're used to the Z table, which has the probabilities in the table, right? Now we have T's in the table. So what we find here is, okay, see here, the T table gives positive values of T, okay, since T is symmetric around the mean of 0. Is symmetric about the mean of 0. So if I paste this and I crop it down and we just focus on 50 degrees of freedom, Okay, so at 50, so at DF equal 50. Okay, so here I am on this line here. What this is saying is that, okay, at the first cutoff of 0.679, the area in one of the tails is 0.25, which means that the area in both tails, so the two-sided p-value is 0.5. Okay, so what we're going to see is we're going to see this. It's symmetric about 0. And the first cutoff here is 0.679. Symmetric about 0, I can replicate that and make negative 0.679. And I have the one-sided p-value is 0.25. But if I have a two-sided test, I have a two-sided p-value of 0.25 times 2. Okay. Same behavior that we've seen before, right? Let's see here. Let's pick another value. 95% is kind of a classic one. So 2.09 here, or 2.009 and negative 2.009. We're told that the area in one of the tails is 0.025 and the area in two tails times 2 is 0.05. .025, 0.025. Okay, so as we move out, right, our t is getting further away from 0, so we're moving further out into the tails, and that's making the area in the tails smaller and smaller and smaller and smaller, right? Same idea as the z-scores. We'll do one last one. Can't remember what this one is, but we can figure it out. 3.261 and negative 3.261. Oops. Has a one-sided p-value of 0.001, 0.001. Times that by 2, I get 0.002. Right? What does that mean? So what's the critical value for this confidence interval, or rather the critical value of 3.261 is what confidence level, right? Well, I have to take away 0.002. So 1 minus 0.002, which is in the tails. So this must be a 99.8% confidence level. And I can confirm it if I just look at the table just quickly here. 99.8, that is where this 3.261 came from. That's at 50 degrees of freedom. Let's scoot over here. Okay, so we can confirm it, but that's how it works, right? And so remove that. Okay, so that's why we have a 95% confidence interval if our critical value is negative 2.009 and 2.009 or plus minus 2.009, right? And at 50 degrees of freedom. So the shape of the distribution changes depending on the degrees of freedom, right? These values would change if we slightly, not much, but slightly if we had 60 degrees of freedom. Right, so on and so forth. Okay, so what happens is there are two ways that we can find our p-values, right? We see the p-values here, one-sided p-values, two-sided p-values. So depending on the question, right, if you have a not equal to sign in your alternative hypothesis, then you have a two-sided p-value, right? If you have a less than or greater than, then you have a one-sided p-value. So it's already laid out for you, so that's nice. What's going to happen though is you're going to calculate a t, and then just like in the chi-squared situation, what happens is we're going to place it somewhere along this line, right? So for a hypothesis test, we calculate a t in step 2. And then to find the p-value in step 3, and to find the p-value in step 3, we place that calculated t, and maybe what I'll do is just to emphasize, I'll write t calc, just to emphasize that that's the one that we calculated. Okay, so then what we do is we find the p-value by taking that calculated t and finding the 2 t's in the table that wrap around that t, right? So we try to place it along this number line, right? So if we know, let's focus on this one here. If we know that it's between 2.009 and 3.261, then I have an estimate for the area in one of the tails, right? It's between 0.001 and 0.025. Notice how you have to read those backwards. A little bit tricky, but once you've got an overview of the t distribution, then it makes sense, right? As your t increases, the area in the tail decreases. So we calculate a t in step 2, and to find the p-value in step 3, we take the t calculated and find the values that wrap around it in, or maybe I'll say in brackets here, at the appropriate degrees of freedom in the table. Okay. Those t values will translate to a range of p values. I know, t's, p's, z's, q's, whatever. I know. Okay, but those t values will translate to a range of p-values, right? Unless we use software, then software can just give us the p-value, but the tables are a little bit less precise. Okay, so those t-values will translate to a range of p-values. We can still use the range, right? So for example, if we're looking at a one-sided test and our calculated t is somewhere in here, right, between 2.009 and 3.261, let's assume that those are the values next to each other in the table. They're not, but let's assume. Then I can say that, well, the one-sided p-value is somewhere between 0.001 and 0.025, which is that less than or greater than 0.05, the alpha level of 0.05? Well, both of those are less than 0.05. So then I have enough evidence to reject H0. And as soon as I have a p-value, or now a range for my p-values, then I can go ahead and I can start stating conclusions and all that fun stuff. Okay, and it all stays the same. Okay, so or use software for precise p-values, right? But for homework questions and for the test, or sorry, the final exam, so this will be on the final exam, not on test 2. For the final exam, then we're assuming that you're using the table, right, and not software. Okay, so let's see here. Okay. Oh, so I'm going to use the example that's in, let me see here. Oh yeah. So all the stuff that we talked about is actually outlined. It's called chapter 5. That's from the old edition. But we talk about the assumptions, and then we talk about the T distribution. We talk about the degrees of freedom. So if you're feeling like, okay, that was a lot, it's all in here and it's all summarized. So, and even using the T table to find p-values, we can do that. Oh, but the one thing that I will say is this is the p-value approach. Remember how we talked about the p-value approach versus the critical value approach, especially for a chi-squared? We talked about it. And so this, we call this the p-value approach. We could, or maybe I'll say alternatively, we could use the critical value approach. We could use the critical value approach. Okay. I'll just underline that so it's blue to match. Okay. So what we do then, the critical value approach says that if we let alpha be 0.05, that's the default. Oops, whatever. If alpha is 0.05 and the degrees of freedom, let's say, are 50, or let's change it, maybe 80. Right, so that's the degrees of freedom, not the sample size. And we are testing, the null hypothesis is that mu is equal to some mu naught, and the alternative is that mu is not equal to some mu naught. This is a two-sided test. So then what we could do is we could zoom in on the table at 80 degrees of freedom. And what we would do is, okay, if I have a two-sided test, then I'm focusing on these guys here. And what I'm going to do is I'm going to force the two-sided p-value to be 0.05 because that's my alpha level. Okay, so then here, oops, see, 0.05 corresponds to a T of 1.990. Okay, which means that a calculated T larger than 1.990 means we have enough evidence to reject H naught, because after this point, 0.05, then all these p-values are smaller than 0.05. We've ensured that. Okay. So if, oh man, come on. If the calculated T is larger than 1.990, okay, then we can see that the p-value would be less than 0.05, right? So because I've moved further out into the tails, so then we have enough evidence to reject H naught. we have enough evidence to reject H naught. So that's using the critical value approach versus the p-value approach. Usually just because I like to stick with the same thing and I like to do the harder one together, I find that the critical value approach is a lot easier to think about. If it's larger than this, then, then we can reject H naught. But we need something, so the p-value gives us a little bit more information. How unlikely was it? Was it just 0.045, right? Or was it 0.00045, right? So how unlikely was it? That's what we can get out of the p-value approach. Okay, so these kind of summary notes outline the steps in general, but then we also have this question worked out. Okay, I think I have, so because I'm running low on time, classic, what I'm going to do is we're going to work through this one, because then I can just talk about it and we can just we can rely on these solutions. So what I've done is everything that you would need for a complete answer. So on the final exam, you will need to do 2 or 3 written questions. Okay, so full written questions. So in order to make sure that you get full marks, you would have to include everything that are in these little boxes. And I've tried to do that for a lot of these notes, although they're, I haven't used them in a little bit, but that's okay. So there is another problem here. And what I'll do is I'll let you work through that one and I'll just post the solutions at the end of these notes today. Okay, so you can work through this this example, and then I'll give the solutions in these notes after today. Okay, so I do want to just cheat and use this one here. Oh. Talk about step 1 first. Okay. So the question is, the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. Sounds important, right? A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. So, and then here are the results. Okay, so we have a random sample, and what we're assuming is, okay, so that satisfies the independence criteria. And the only thing that we're assuming, we assume that this follows a normal distribution. We could make a histogram of these data points, but I have failed to. Okay, so in terms of the conditions, for independence, it was randomly selected. Really shortcutting here. For the normality, N is less than 30, but normality, we can assume we assume a normal distribution, but we assume an approximately normal distribution. Okay, so I forgot to include that, but there it is. So I've calculated the sample mean and the sample standard deviation. Okay, then the question follows up with, a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Now, the thing is, 4.771 is less than 5, but what we want to know is if it's significantly less than 5. Okay, so the null value is going to be that 5, right? I have sample information, and what do I want to compare it to? I want to compare it to 5. Okay, and so our null hypothesis is that mu equals 5. It's not significantly different from 5. 4.771 is close enough to 5, right? Or what we're concerned about, and in this case, we're concerned about one side because it doesn't seem to matter if it's higher than 5, right? But we are concerned if mu is less than 5, and so that's our test. Now, this is a one-sided test since we're only concerned with mu being less than 5. So the one-sided test comes from this here. Okay. So it comes from the alternative hypothesis, and that always throws people off. Okay. Once I have, oh, that's something else. Once I have my null and alternative hypotheses, then I can go ahead and calculate my test statistic if I'm doing a confidence or a hypothesis test. Okay. We could just as well build a confidence interval, but it's really no different. And you can use a confidence interval to test the hypotheses, just like we did with proportions. And so all that stuff that we've learned, it translates, but now the t distribution instead of the z. And that's really, you know, the only main difference. So to calculate the t, we have x bar. So that's our point estimate minus our null value divided by the standard error of x bar, which is s over root n. So once we calculate our t, we find that t is approximately negative 0.944. Okay. So to find our p-value, and I'm going to have to do this in 2 steps here. We need to first drop the negative, right? Because our t table only has positive values for t, but that's okay. So what you would say is you would say using the t table, you tell me what you're doing with degrees of freedom equal to n minus 1, which is 15 minus 1, which is 14. And this seems excessive, right? But it's also not that much work. And you're really covering your bases. What if you misread n, right? What if you misread 15 and you said 51 and then you use the wrong degrees of freedom? Well, at least if you told me that this is how you did it, that's correct, right? And then how are you supposed to know that your degrees of freedom was wrong? Whereas if you just tell me the degrees of freedom is 49, for example, or something weird, then I don't know where you got that from, right? So here, better safe than sorry, and just outline everything that you're doing, okay? And so what we do is I have a negative value for t, and to drop that negative, I take the absolute values, right? And so that's what those vertical lines are. So I take the absolute value of my calculated t, which you can denote by t calculated just to match what we said before, right? And then what we do, so if I'm writing this by hand, what I do is I put my calculated t in absolute value brackets, even if it's positive. There's no shame and no harm in putting in the absolute values. So I put that in the center of my page. And then what I always do is I put less than, because it's going to be between 2 values, right? And so even though this looks complicated, if you just always follow the same route, then you're fine. Okay, so you put your calculated t in the center of your page, put absolute value brackets around it, less than on either side. And then you take your 0.99 or 0.944, you try to place it along the 14 degrees of freedom line. Okay, and what you're going to find is that it's between 0.868 and 1.076. Those are the 2 values that wrap around 0.944. Okay. Then what you do is you trace down to the p-values. Now remember, we need a one-sided p-value. So again, I put that in the center of my page below my calculated t, and then I've got a range for my one-sided p-value as well. Okay. All we know here is that the p-value, the one-sided p-value, is somewhere between 0.15 and 0.2. I can still draw conclusions from this. And it won't happen that the 0.05 is somewhere in here, right? Even if it did, you wouldn't have enough evidence to reject H naught, but that's not going to happen. Okay, so the one-sided p-value is somewhere between 0.15 and 0.2, which I don't have enough evidence to reject H naught. Okay, because both of those are above 0.05. So for the conclusion, right, we said alpha is 0.05. That's also the default. But this is all mandatory, right? Just like before, you have to state your conclusion in terms of the null hypothesis. First, you have to compare your p-value to the alpha level, then your conclusion in terms of the null hypothesis, and then your conclusion in terms of the question. Since our p-value is between 0.15 and 0.2, it's greater than our alpha point equal to 0.05, which means we do not have enough evidence to reject H naught. Therefore, we don't have enough evidence to conclude that the mean dissolved oxygen level in the stream is less than 5 milligrams per liter. That's a good thing in this case, right? We didn't want to reject the null hypothesis, but we have to do the test to see what's going on with the water, right? Okay. So same three components that we had to use before, right? Compare your p-value to the alpha level. So compare, oh, it is that zoomed in. Compare p-value to alpha, then conclusion for H naught, right? Do you have enough evidence to reject H naught or no? And then the overall conclusion. Okay. There are a couple of different R codes here. So what you could do is you could calculate things by hand. Here I'm just inserting a data set. We haven't used R that much for proportions because it doesn't do well with proportions. Okay, but now we're going to start to use R for our t-tests. So here we could do it by hand by just programming the calculations. Or if I enter my data set, okay, then what I can do is I can use the t.test command. Oops. So here, whoa. I enter my data. Sometimes you'll have data given to you, you'll have a data set, but for small data sets like this, then you can just enter them using the C, which is concatenate. And then using the t.test command, I give it the data set. I give it my hypothesized value. The null value, and the alternative in this case is less, right? And that's the alternative hypothesis, which I think is obvious. So the t.test command runs a one sample t-test comparing the sample mean to 5. Okay, you find that the t is negative 0.94256. Why is it different than what we found? We were rounding, right? We rounded our mean and we rounded our standard deviation. And that's what's going on here. That's all. The degrees of freedom is still 40. And the p-value we find is 0.1809, which is between 0.15 and 0.2. But now we have a more precise value. Okay. It also gives the confidence interval, but unless we have a two-sided test or I think it's two-sided here, it'll only give one side. So you have to do a two-sided test to get the confidence interval. But I see that I'm way out of time. And so if you have any questions, let me know. Otherwise, I'll post the the solutions to that other example, the following example, so you can work through it and check it on your own. All right, 2 sample tests next day. Any questions, let me know. Otherwise, see you Thursday.